So good morning again. I don't know if it is working, this microphone. Yes. So we will start double voice. But okay, that's fine. We will start with the next speaker, Enrique Pardo, from the University of Cadiz. And the talk is about modeling groupoid algebras using left cancellative small categories. So I will close now.
Okay, thank you. Can you hear me? If so, I'll start by thank the organizers for giving me the opportunity of giving this talk in these conditions. I'm so sorry. And as you can see by the title, what I pretend to do is to, sorry, 1 minute. Okay. It's to show you a way of constructing groupoid sister algebras by using left cancellative small categories. First, the contents of this talk is a few part of the joint project that we carry with Eduardo Ortega that talked yesterday, and that can, at the moment, appears in these two papers that are published. If you're interested in them, you can ask either him or me for then some commercials. The first paragraph is about the people that paid for me participating in this research. And second paragraph is about the people that paid for Eduardo and I attending this meeting. In particular, thank you, Paquito and Fernando. And now let's go to the movie. The first I'll do is to outline more or less quickly what I'm trying to do. First, I try to motivate what's the interest of modeling groupoid sister algebras using categories. Then I'll quickly recall what's a groupoid, topological groupoid, and the algebras that are associated. I'll say the basic I need about left cancellative small categories in order to go to the main result in the talk, that is to explain how to construct the tag groupoid associated to left cancellative small category, and then to construct also the corresponding sister algebra. And hopefully, optimistically say, if I can say something about subset products, I'll do that. But just start a movie, and then I'll start with motivation. When we work in any topic, in particular in sister algebras, we're interested not only in proving theorems, that it's beautiful, but also in showing that the results has, say, control scope of their usage by having a large amount of families of examples that allows us to polite and refine the results. In the last 30 years, 40 to be precise, a concrete technique was developed in sister algebras in order to produce sister algebras, even in terms of generators and relations, associated to some combinatorial objects in such a way that you can use the properties of the combinatorial object in order to characterize the properties of the algebras. The first well-known sample is that of Kurtz-Krieger algebras that were introduced in the early 80s by Joachim Kunz and Wilhelm Krieger, and that were, say, encoding the information of subshifts of finite depth, so of symbolic dynamics, to describe a very interesting family of sister algebras that gave rise to the study of purely infinite simple sister algebras, a very important class in theory. But since the object that they use are very restricted, also the class that you can represent was. And in the early 90s, Kunz, Paz, Reiber, and Renault extended the scope of Kunz and Krieger's construction and say defined sister algebras that they were associated to row finite countable graphs in such a way that algebras were given in terms of generators and relations encoded by the graph, and also the properties are encoded in terms of the properties of the graph. So you can characterize when the algebra is simple, that is a algebraic and topological condition, just looking at a couple of clearly easy to see in the graph properties. Moreover, because Jean Renaud was involved, they showed that these algebras also can be represented using topological groupoids, what now are called the Koenig-Renaud groupoids. And that's good because you can then study the properties of the algebra, not only looking at the, say, combinatorial presentation in terms of generators and relations, but also by using the well-known theory about algebra associated to groupoids. But also this family of algebras was too restrictive. When they started to compute the K-theory, the K0 and K1 groups, they realized that they cannot cover all the possible models of sister algebras, even for purely infinite simple ones. And then they started as a strategy of adding extra properties to the combinatorial object in order to extend the scope of the construction. And then you can find historically ultragraph algebras, lovely graph sister algebras that are associated to suffix shifts, high rank graph sister algebra that generalizes the buildings of Robertson and Sticker, Katsura algebras associated to a couple of integer matrices, finite or infinite, with few properties, algebras that can be easily distributed and studied, also Nicosevic algebras that are associated to self-similar actions of group form trees and their generalization to self-similar graphs where the action is given by groups and then by groupoids on finite and infinite graphs. In any case, all these families that extends the construction of graph sister algebras share some common characteristics. They can give properties of the algebra just looking at the combinatorial properties of the underlying object, and also they can be, say, represented as algebras of étale groupoids. The problem is that the zoo was going large and large, and then at the early 2000s, Jack Spielberg decided to boil up the common properties of all these models, and he concluded that the way of working all that stuff in a unique way is to use algebras associated to left cancellative small categories. I will define that in a minute. And what he showed is that not only extends the previous classes and give the presentation in terms of generators and relations, but also he was able to show that there is a groupoid in such a way that the sister algebra of the groupoid coincides with the sister algebra that he defined for the left cancellative small category. So the key point is that representing algebras using groupoids is an important tool. In another approach to the same situation, you can study the work of Alan Patterson in the middle 90s that he can generalize the algebras associated to universal representation of groups, so to algebras associated to symmetries, to the context of inverse semigroups, so the partial symmetries of the spaces. And he showed that you can define for any inverse semigroup a universal sister algebra associated to the representations of this inverse semigroup. And moreover, he showed that he can, say, canonically associate a groupoid, that very well behaved groupoid, an ample groupoid, such that the sister algebra of this groupoid turns out to be the sister algebra universal for the representations of the inverse semigroup. The problem being that since the representations are semigroup representations, only keep track of the multiplicative relations, and then you cannot encode the additive relations that are needed to represent graph sister algebras or the other models. You only can represent the Toeplitz algebras. The way of solving this problem was found by Rui Excel that at 1998 showed that you can take a restriction of the Patterson's groupoid just by restricting the action of the inverse semigroup to a invariant closed subspace of the space of where you are acting to construct the Patterson groupoid. And then when you consider this new groupoid, the groupoid, then you can recover for the universal representations of this kind of groupoids, you can recover the CK2 type relations, the additive relations that were lost in Patterson representation, and then you can represent graph sister algebras, ultragraph sister algebras, etc., using these groupoids. Moreover, the key point is that Rui Excel showed that any second countable ample groupoid is a large family. Are not all the groupoids that are used for defining sister algebras, but almost. Or any second countable ample groupoid can be represented up to isomorphism as a type groupoid of a suitable countable inverse subsemigroup of the groupoid. So there is a large class of groupoids that can be studied using an inverse semigroup approach. Then the natural question is, which is the connection between Excel, Job, and Spielberg's construction? There is any connection? And the answer is yes. And the first step was done by Don Millen, Lalonde, and other people that started by showing that when you have a life cancellative small category, you can associate what they call a zigzag inverse semigroup. And moreover, that any inverse semigroup is Morita equivalent, almost isomorphic, to the zigzag semigroup for a suitable single aligned left concellative small category. So a left concellative small category that is very well behaved, and what they did is to explicitly construct this left concellative small category. So what they are saying is that you can represent any uh, groupoid that is ample as the tech groupoid of the inverse semigroup of a left conservative small category. But the point is that when this is finally aligned, the category is finally aligned, that was the first result of Edward and I, then the C-star algebra defined by Spielberg is the C-star algebra of the tech groupoid of this inverse semigroup. And this is essentially what I'll try to explain you in this talk. Certainly, that means that Spielberg algebras model algebras for second countable groupoids, and also means that because of the approach of Eduard and I, we can use a technology developed by Rexel and myself some years ago in order to determine the properties of the groupoids and then of the algebras using looking at the combinatorial properties of the categories. In our project, we were centered mainly into things, subset product, that is a way of defining self-similar actions of groups or groupoids on categories. And also we were worried about the amenability of the associated groupoids in these constructions because amenability guarantees that the C-star algebra, the reduced C-star algebra, and the full C-star algebra of the groupoid will coincide, and this is important for using tools that work in one of the sides or other of the sides. Now, let me recall quickly what a groupoid and their algebras. A groupoid is a small category in which every homomorphism is an isomorphism, is a group with a lot of invariables, with a lot of units, but not any pair of elements can be say operated. And you can define by using the say the inversion and the multiplication of the groupoid, you can define range and source maps from the groupoid to the set of units, that is the space of objects of your category. When the groupoid has a topology in which the operations and then the range and source map are continuous, we say that it is a topological groupoid. And when these range and source maps are local homeomorphisms, then we have an étal groupoid. We'll concentrate in étal groupoids such that are locally compact and the unit space is Hausdorff in the relative topology. Are the more common ones, and usually they are, equipped with a Hermitier, so it's very good. And when we stress the conditions on the unit space of an étal groupoid, and we ask the groupoid to be the unit space to be zero-dimensional, so say totally disconnected, then we have what we call an ample groupoid, and this is the kind of groupoids we will work with. Once you have an étal groupoid, you can consider the linear pair of set of continuous complex value compactly supported functions on G, then define a convolution product. Here, the only problem is to prove that this, say, sum is finite, but this is true because some compactness conditions that applies. And also you can add an involution on this set of functions. So you can endorse this set with the structure of complex star algebra, and then taking suitable norms, you can construct a full and a reduced C-star algebra associated to a groupoid. I will skip all the nasty details, and I'll skip to the left concellative small categories. And then in this case, what we have is that a small category is essentially a category in which the objects and the morphisms are sets. You can consider for a model in your mind, you have a directed graph, then the vertices are the objects, and the finite paths are the maps. And then with this idea in mind, you say that the source of a map is its domain, and its range is the range of the map. And we fix the right invariable elements as the maps that has a right inverse. Left cancellative means in this context that when you have alpha beta equal alpha gamma, then you can say erase alpha. And categorically, that means that all the morphisms, sorry, in this category are monomorphisms, and in particular that right, left, and to say that the invariables coincide. If you want to skip inverses, then you must restrict to the situation where the only inverses in your category are the units or the objects. Then, in order to do some theory, meaning what's done for graphs, rank graphs, etc., you need to consider the notion of extension of a map, and essentially beta extends alpha. If beta it's factor out through alpha, being alpha the first map the last map that you're using. And we denote by this in this way the set of initial segments of the factorizations of any map that endows your category with a partial order. We also need the condition of common extensions that makes sense if you think in maps. So you're mapping from one set to another, and then if you're going through this source and range sets through factorizations, but if these factorizations of the map coincide with the original one, then the original maps that you're putting in first site are exactly the ones that has as common extension the map from the source to the target. It's something like that. And then under mild conditions, you can ask the existence of, say, minimal common extensions. And using this idea of minimal common extension, you fix the property of being finally aligned that is satisfied by mostly of the examples I put it. And category is finally aligned if whenever you have two maps, then there's a finite subset that the common extensions are generated by extensions of this finite family of maps. When the set of maps that are common extensions is singleton, then we say that is singly aligned. And finally, in order to express the algebras of Spielberg, I need to talk about what is an exhaustive set. So I fix the notation alpha intersection beta when they have a non-empty common extension. And we say that a subset of a set is exhaustive in the big set. If whenever we have an element, a map in E, then it has a common extension with at least one element in the subset S set. And we will need to fix all the finite exhaustive subsets of any element in your category. And now let me talk about this tag groupoid. So the algebra defined by Spielberg is the algebra universal algebra given in terms of generators and relations, where the generators are associated to the category, and the relation says the first one that all the elements, all the generators are partial isometries, and if alpha is a object, then are projections. That it keep track, second relation, of the composition of morphisms in the category. The third says that range projections set to morphisms in your category decomposes as a supremum of the projections set to the minimal common extensions of alpha and beta. And this is what is called CK1. And CK2 says that the projections set to any object factor out as the supremum of the range projections associated to any family of finite exhaustive sets starting in B. This is the presentation, and this while up the presentation of all the algebras in the large, say, list of families I've presented. And what he did was associated an ample groupoid to this presentation, and he showed that the full sister algebra of this groupoid corresponds to the above algebra. And what we do is to take advantage of the picture of Riexel that you can represent any groupoid, in particular Spielberg's one, as a groupoid of a tag groupoid of an inverse semigroup. And then, but we will show is that this inverse semigroup that appears in the case of Spielberg's model is exactly the 6F semigroup of Donsick and other people. So let me first present who is this inverse semigroup. You pick any left cancellative small category, and then you define partial bijections into the category that goes from alpha lambda to source of alpha lambda is a destruction operator, and from of alpha to S to f of alpha lambda to alpha lambda, that is a construction mapping. And then since these are partial bijections into lambda, and the set of partial bijections is our set is always an inverse semigroup, you can produce the inverse semigroup generated by this two operators. In the case of finally aligned left cancellative small category, the elements in this semigroup has a very helpful presentation, but I'll skip that. And now what I need is to construct the groupoid. And for constructing the groupoid, I need to construct data importance on this inverse semigroup, then the filters, then completing the topology, the ultrafilters to get the tag filters, define a action by partial homeomorphisms, and then construct a groupoid. But this is quite involved, and what Eduardo and I did was work directly with the category, skipping idempotence and skipping also filters, etc., and replace that by a space of hereditary upwards directed subsets of your category. Hereditary means that inherits to be in the set if they are dominated above, and that and any pair is dominated above by someone. And then we equip this set with a topology that turns out this set a locally compact Hausdorff total disconnected space. And then we define which are the maximals. And since we have a topology, we complete the maximals, and we talk about the, say, tight hereditary upward directed sets. The point being that the set of hereditary and upward directed sets is homeomorphic in this topology to the subspace of prime filters of the left of the inverse semigroup of lambda. And then you can extend that in such a way that you can show that the maximal sets are homeomorphic to the ultrafilters, and then the tag hereditary sets are homeomorphic to the tight filters. So we are encoding in a more say friendly way the construction of Reaxel, and then in this case it can be easily construct a model of the action of the elements of the inverse semigroup on the elements of this set lambda star. The formula is like that. And because this induces partial homomorphisms defined by the action of this S from the domain to the range of the action. And the action is continuous and extends not only to the ultrafilters, but also to the tech filters. So it's the same in our language. And then we can define what is called the transformation groupoid of this action, that is a set of pairs as F, where F is a set that is in the domain of the action of S. The range and the source are clear how are defined. The product is defined when it makes sense, when they connect, and you can define the inverse. So you get a groupoid that is a ample groupoid. And then in order to avoid redundancies, you factor out through the germ relation. That means germ relation essentially is to say that SF coincides with TG if G, F, and G coincides as sets, and then S and G, so S and T as partial homeomorphisms coincide on a neighborhood, open neighborhood of the element F. Then you factor out, you get this groupoid that is, by the construction that we did, is the tight groupoid of the inverse semigroup in Excel terms. And then what we did, and was the most difficult part of our result, was to show that this groupoid is topologically isomorphic to a groupoid defined by Spielberg. That was a very, very involved construction, that of Spielberg, so you cannot compute effectively the groupoid or say anything. And then using that and results of Reaxel and myself, then we were able to say, characterizing combinatorial properties, in terms of combinatorial properties of the category, we were able to characterize properties of the groupoid, and then, for example, to characterize when the sister algebra of the groupoid, groupoid associated to this category, is a simple algebra. We did more things, but that was okay. And I think that my time's over. So I only signal that there are two typical examples of application. One is change the construction of Rabun and all that people about graph sister algebras. And then if we change the graph construction by the category of finite paths, then we obtain a better picture of graph sister algebra in terms of groupoid sister algebras. And same happens when we study the construction of higher rank sister algebras by considering the category of finite words on finite paths on the category. And I think that's all I want to say because my time is gone. So thank you for your attention. And if you have any question, I'll say open. Okay. Hello. Are you listening
Thank
to me?
you, Enrique, for your talk. Are there any questions or comments? No, I have a small question. Perhaps it's a rather appropriate question. I do not know. But you, at a certain point, can I remove
Could you repeat your question, please?
I don't know if this one works. Are you able to listen me, Enrique? No. Are you able
Yeah,
to listen?
yeah. I listen to you.
Okay. I have a question. It's perhaps not appropriate question, but at a certain point, you talked about graphs,
Yes.
and graphs have many applications on networks and many other structures. Do you know if in particular this
Uh,
abstract theory is important at the level of some particular applications?
as far as I know, the answer is no. We're all interested in the graphs just in terms of say picture, the generators and the relations of the algebra we were working with. But we are not really interested in the properties that are interesting for people that works in graph theory. In particular, we're working all the time with directed graphs, not undirected ones. That means that for applications to networks, to electrical sources, to all that stuff, the results we work with doesn't apply at all. I'm sorry.
No, thank you very much. Thank you very much. So we thank you again